Venn diagrams is a method by which we can visualize pieces of data that belong to different categories. Usually you will see these represented by circles, also known as sets, and they are likely to be intersecting or overlapping in some way. With these then, if a piece of data then fell under both or however many categories, it could be shown to be doing so by being placed in an overlap such as this, where it's saying, okay, it's both in the circle for this category and the circle for this category. If, however, it only fit into one category and not the other, then it would just be put in the region that isn't in the overlap, yet still in that respective circle. And if it was in neither category, then it would just go on the outside. Now, if we're then looking at diagrams like this, we're going to want notation to help us refer to which sections of the diagram we're talking about. So, when we are looking at the overlap, in this case specifically of set A and set B, this could be represented as A intersection B, with the intersection symbol being this kind of N or archway shape here. Alternatively, if we wish to refer to everything inside of either A or B, so either rather than and/both, then that's going to be union, with the symbol now the other way up, more like a U shape. So in this case, it doesn't matter if it doesn't fit both criteria. So long as the piece of data falls into one of them, it would be counted. And yes, this does still include the intersection. There is actually another way of thinking about this, and you could say that this is the same as A add B minus the intersection. So if you took the entirety of circle A here and added all that up, and then took the entirety of circle B and added all of that up, to do that you would have counted the intersection twice, and you don't want to double or triple, depending on how many circles you have, count a certain thing, so that's why you always just take away the intersection again afterwards, just to make sure you only have one lot of whatever this is. This can help us if we're doing more calculation-based questions, which we will be doing later on. Before that though, we'll now look at our third main bit of notation. This is where we may be looking to identify part of a set that is not in the overlap. Now right now for this notation, not only will it give you that region, but it'll also, if you notice, give you the outside as well. This is essentially the not notation. Now this is represented by an apostrophe, and this can be printed somewhat small, so you want to make sure you're looking out for it in your questions. But if we have the letter that is labelling the set with an apostrophe afterwards, we're saying everything that is not that thing. Now, if you did specifically just want that region that's only the other set, and you didn't want to include this outside as well, that's when you'd now need to bring in the intersections. This would be not A intersection B, so what is simultaneously not inside of A, yet also exists in B. That is just this bit here. If, however, you were to use the union symbol, this would be an example of how union can actually be a little tricky, because for union, because we're looking at just anything that fits either description, you can have a contradiction. In this case, if we were to shade in everything that's not A, well, that would be everything that's currently put in grey there, but then have union B, because then once we've done this not A, we'll now do everything that's B. That would get you to also include the intersection, because that is B. And it doesn't matter that this intersection is inside of A, because it fits that second description. So if you have a union question, what I basically just suggest is that you identify everything that fits the first description, and then once you've done that, then separately identify everything that's in the second description, just in complete isolation. Don't worry about how that interacts with the first description. Again, for all of these, we'll get more practice and examples of those as we go into the questions in a moment. But for now, these are the main concepts that you'd need to worry about in AS for Venn diagrams. As you move into A2, there is another piece of notation or another concept that you will want to be aware of, and that's just of given. So we have A given B, which is represented by this vertical line here. Now, this is somewhat more difficult to represent in a diagram, which is why I haven't elected to try to do that here. Instead, what we may wish to do is show what it's the same as. And so A given B. would be the same as the intersection of A and B divided by B. So the intersection of the two notations divided by the right-hand notation. This is going to come up a lot more when we're looking at probabilities to do with these things. And the ramification of this basically is usually you'll be looking at whatever the notation is out of everything. So out of 1 if it was a probability-based thing. However, here, if you're now given something, you're reducing your focus to whatever that second thing is. So in this case, if we had A given B, you wouldn't be looking at the entire diagram anymore. You would just be looking at the circle B, and then within B, you'd be saying, okay, which part of that is also inside A? So in this case, that would again be just the intersection, but would be ignoring the outside and this part of A here. If those are your notations, there's also some phrases that again you'll want to be aware of. The first of these is mutually exclusive. Now, if two events are described as being mutually exclusive, that means that one cannot happen if the other does. One stops the other. So if you had two numbers and one of them was odd, you couldn't say that it is also even. Odd and even are mutually exclusive criteria. If this happens, then from a notation standpoint, we would be saying that the probability that there is an intersection between, in this case, A and B, that would be 0. The other phrase is then independent. Now, if things are independent of each other, you might think that means, okay, one can't happen if the other happens. They're completely separate circles, that they wouldn't have an overlap. Well, the problem with that is that we already have a term for this. It's mutually exclusive, so independent has to be something else. What independent means is one does not affect the other. Well, how is that different from what we just had above? That would be like saying, was mutually exclusive, was if something is odd, it can't be even. Independent would be whether or not the number is odd or even doesn't impact whether it's positive or negative. Both are two different criteria sets that you could describe a number as having, but one is not impacting the other per se. I guess in this case you could try to be awkward with 0, but it's just an example. In the examples that you will be getting in your actual questions, the two things will usually be completely separate from each other, no other connection. Otherwise, at least that's what you're trying to check for. Again though, just to get down our notation, in this case it is going to be a little bit more of a formula, and it is one that we can use to test for independence, which can be a part of questions like a part B or a part C. If events are truly independent, then the probability of the first event times by the probability of the second event would be equal to the probability of the intersection. If, when you put in the numbers from the question into this formula, it doesn't work, like this side doesn't equal this side, then you've shown that they're not independent, that one is in fact actively affecting the other. It's either making it more likely to happen or less likely to happen. With all of this in mind, though, let's just start to look at some actual questions. So we might start off with something like this, where we're given a description and we have to fill out a Venn diagram based on it and then solve for some unknowns. So if we just read through said description, first we have, given that the probability of A intersection not B is P, the probability of A intersection B is the same as the probability of B intersection not A intersection not C, which is 0.1. The probability of B intersection C is 0.05. Probability of not B intersection C is Q. The probability of A intersection C is 0. And that the probability of C equals 0.2. Also, given that A and B are independent, find the values of P, Q, and R, and then say whether B and C are themselves independent. Well, to start off with, we're going to want to label these sets. Now notice that obviously this circle in the middle gets to intersect with both of the others, yet these two then don't touch each other. So to determine how we're going to label each, I mean, most likely it's just going to be going A, B, and C, but we'll double check. So we've got A intersecting with B, and C intersecting with B as well. Okay, so B is going to be this center circle here, with this then being A and C, and yes, consider there is no intersection between A and C. That is making them mutually exclusive from each other. They're not overlapping, so yes, it's just going to read from left to right. Then, so if your A intersection not B, well, which part of this diagram is simultaneously in A and not in B? That would be this bit here, so that's P. A intersection B is the overlap of A and B. And then B intersection not A, intersection not C. Well, what's within B but isn't in A or in C? Well, that's just this bit here. And both of these we're being told are 0.1. Then intersection of B and C, that's just this bit here. That's 0.05. And not B intersection C. So what's in C but also not B? Well, that's just this bit here. That's Q. And then for now, we're not necessarily going to label that because that's the whole circle, and there isn't a clear way of labeling the whole circle. Just bear that in mind for now. So, when working out the remainder of these unknowns here, and to be clear, that R is just this bit on the outside, because they're probabilities, they have to add up to 1. So once we've worked out our P and our Q, if we just do 1, take away everything that's there, that will leave us with what has to be on the outside. To work out P, first of all, because that's the first one alphabetically, it's the first one given to us, we'll look to the fact that A and B are independent. And from our formula down here, we know if we were to take the probability of being in circle A times by the probability of being in circle B, it should give the intersection here. Well, it definitely will if we're told that they're independent. So in this case, because these are already probabilities, we could just go straight into plugging them in here. So the probability of being in A is the sum of P and 0.1. Add them together will give you the whole circle. Times this by the probability of B. Add up all the probabilities that are under B. That's going to be 0.25. And we know that then has to equal this 0.1 in the middle. Rearranging this, you get that P is going to equal that 0.1 divided by the 0.25 minus away the 0.1. That's going to leave you a P being 0.3. Then for Q, because we know that the entirety of C is 0.2, that these have to add together to make that, if you just do 0.2 minus the 0.05, that leaves Q being 0.15 here. And lastly, to work out, well, lastly for this first bit, to work out what R is, if we were just to do 1 minus all of these, that would leave you with R being 0.4. Now then, to work out if B and C are independent, you may notice we didn't actually need to do this first bit to answer this piece of the question, because we already know, well, we can work out what the entire probability of being B is, and we already know what the entirety of C is, and we already know what the intersection is. So simply, if you just put into your calculator the 0.25 that is B times the 0.2 that we know is C, does that equal the 0.05 of the middle? Yes, it does. Therefore, these two are indeed independent. So, with that in mind, let's just see how you might get along with a first example of your own. Now, this down here is very much like what we just had above. However, the notation has already all been given for you rather than being given in a description sense, or for the most part. So here we again have 3 sets, A, B, and C. We have here, this is a quarter, 3/20ths, a tenth, and then P, Q, and R once more as our unknowns, although they're in slightly different places. Once again, A and B are independent, and now we know that the probability of C is 3/10ths. So based on this, find P, Q, and R. Think about how we've been doing this in the previous example, pause the video, have a go for yourself, and then press play again when you're ready to compare. So, to begin with, let's start by trying to work out P. This time we do definitely have to do it in this order. Before, I suppose we could have worked out Q first, but here, while we know that the entirety of C is 3/10ths, we have no idea how they're split up without working out P first. And I say P because it's also related to other circles. So if A and B are independent, and we're to use the formula that we had before, we can say that the entirety of A, which in this case, if you were to do a quarter, add 3/20ths, would give you 8/20. And you have to times that by the sum of this circle here. So 3/20 add 1/10. Well, that's going to be 5/20. And this would be added to P. We don't know what P is. But because we know for certain they're independent, that's going to equal the 3/20 here. So just to make P the subject, if we now have 3/20 divided by the 8/20 and you minus the 5/20, well, that's going to leave you with P being 1/8. Now that we know that P is 1/8, now we can do, to get Q, 3/10 minus the 8th. That leaves you with Q being 7/40. And finally, to do R, if we now just had 1 minus all of these, that would leave you with R being 1/5. If we're all right with that, we can see how we've used the principle of independence to work out missing unknowns, and then do like 1 minus or a number minus the other fractions to leave us with the remaining unknowns. Let's just go on to look at some other examples. So here again, we're about to have some description and we're going to fill in the Venn diagrams based on it. However, this time, all three of these sets intersect. They're not using notation, but rather purely statements to give you the numbers, and it's not as clear which numbers have to go there initially. And then also, once we've done this, we'll now have a look at a given that situation from like what we had in the initial breakdown of our notation. So, just to read this through, of 160 customers at a cafe, 99 had a sandwich, 42 had a drink, 30 had crisps, 8 had both a sandwich and a drink, 10 had a drink and crisps, 6 had a sandwich and crisps but not a drink, then 5 had all three. How many didn't buy any of these options? Well, while we don't have to necessarily draw out a Venn diagram for this, obviously I've already given the sets here, but it's quite possible the question wouldn't give you anything, just a load of blank space. While it doesn't explicitly tell you to use Venn diagrams, they're going to be very helpful to get you to represent this, to help you visualize which numbers are going where. When you start to fill this sort of thing in, I will always suggest working from the center outwards. Look for where the intersection of all three is. So in this case, because 5 had all three, 5 is going to go in here. Then for the other intersections, we have here that 8 had both a sandwich and a drink. So find sandwich and drink, that's S and D. The overlap of those two circles is this whole thing here. That includes this 5. So if 8 are in this whole intersection, we've used up 5, that only leaves 3 to go in this overlap here. In a similar principle, 10 had a drink and crisps. Well, drink and crisps, their overlap is here. If it's 10 in total and we've already used up 5, that leaves another 5 just having a drink and crisps, but not a sandwich. However, with the third example, we have 6 had a sandwich and crisps, but not a drink. Because this part has specifically stated this does not include anyone who had a drink, that's only looking at this bit of the overlap here. So the whole 6 goes in this bit here. If it doesn't say not the third criteria, then it involves the middle. If it does specify, then you can just put the number straight in there. Now we can go to the larger circles. So in this case, if 99 had a sandwich in total, so this is the sandwich circle, yet we know that 99 includes this 3, this 5, and this 6. If you just do 99 minus these numbers, that leaves you with 85 going in this section here. 85 people only had a sandwich. Next, if 42 had a drink, well, because it doesn't specify not having anything else or not only having a drink, then that's going to include these numbers here. So 42 minus these leaves you with 29. And then lastly, if 30 had crisps, 30 minus these numbers leaves you with 14 here. To wrap up with, because we know that there are 160 customers in total, if you were to add up all of these numbers inside the sets, you'd find that doesn't equal 160. There'll be some number left over. In fact, there's a disparity of 13. Therefore, this 13 must be what's on the other side. These 13 customers ordered something completely different that wasn't one of these 3 options. So, now that we know this, now that we've answered this first part, we can move on to the second, which is that given that a chosen customer had a sandwich, find the probability that they also had exactly one other item. Well, because we're now given that they had a sandwich, we're not looking out of everyone in the cafe now. We're just looking at who is inside this circle here, any one of these 4 numbers. Out of this group, out of this 99, who had exactly one other item? Well, one other item, so it can't be the people who just had a sandwich, and it can't be the people who had everything. They can't have had all 3. To have just one other, it's either they had a sandwich and a drink, or a sandwich and crisps. Together, this could be 9 people in total who potentially fit that criteria. So 9 out of that 99, which will simplify to 1 over 11. Now, when it comes to these questions, you may not always have the Venn diagrams to work with. It might just be focusing on the notation instead, to be more calculation-based questions, the kind I alluded to before when talking about the given that notation. So up here, just on the right, we could have, we're simply told the probability of A is 5/16, probability of B is a half, the probability that A given B is a quarter. Well, based on this, find the probability of A intersection B, the probability of not B given A, and then the probability of not A union B. And once we have all this, we want to determine if A and B are indeed independent. Well, in order to have a go at this last step, we'll need the intersection in order to compare to the multiplication of the 2 individual probabilities. Where is the intersection? Well, that's the first step. So let's start from the top. Now, immediately, because we don't know if they're independent yet, we can't just times together these 2 probabilities to get an answer that way. Yet we're very limited in what else we can do to try to create this bit of notation. We can't get it directly from either of these, so we must turn to the third one. Now, if we remember from before, I said that this given that notation can be rewritten as the intersection of the 2 letters divided by the probability of the right-hand letter. Well, we know that the probability of B is a half, and we know that this fraction equals a quarter. Therefore, if we just rearrange this, to get this probability of the intersection on its own, if we just do this quarter and times up the probability of a half, that leaves you just with the probability of the intersection being 1 over 8. Now, ahead of this next one, I am actually just going to sketch out a Venn diagram. Anyway, again, even though the question isn't explicitly asking for it, it just helps to visualize. In this case, we now know that that intersection is going to be that 1 over 8. And now with this, we can say that just the A on its own is going to be that 5/16 minus this 1 over 8, which in our case is going to be 3 over 16. And then here for this part that's just in B, that will be the entirety of B, the half, minus the intersection of an eighth. That leaves this being 3 over 8. At this stage, even though it's not explicitly asked for, we could work it out as well. We could also just work out what's going to be on the outside. If you did 1 minus all of these, that leaves the exterior being 5/16, just like the entirety of A. Well, now that we have this, it may be easier to identify what not B given A is going to be. Again, we could do this just with the calculations by saying that this will be the intersection of not B and A divided by the probability of A. We could work out all these numbers just numerically, but looking at it here, just focusing on A now, because it's given A, which bit is also not B? Well, that's the 3/16. So it's your 3/16 divided by the entirety of A, which was your 5/16. Therefore, this will just simplify to 3/5. Now, as for not A union B, this is one of those examples of contradiction that I was again mentioning earlier, when these two criterias don't quite line up. If we were to identify everything that is not A first, so that's going to be the bit that's just B, as well as the outside. So basically we have the 3/8 that is just inside of B, and the 5/16 that's out here. Then we turn to the right-hand side of the union symbol, so this is the B. We've already shaded in the 3/8, but we're also now going to have this 1/8 here. It doesn't matter that that intersection is inside of A, thus contradicting the left-hand side, because it meets the right-hand side criteria. It just has to match one of them, not both. It's not an intersection symbol. Well, now that we have this, we'll just add up all of the fractions that do meet that criteria, basically everything except the 3/16. Or so you could do 1 minus that if you wanted. Either way, so the 5/16 add 3/8 add 1/8, or 1 minus 3/16, that gets you this probability being 13 out of 16. Then, just for that determining of independence that we were talking about before, we've already addressed that we need the intersection between A and B, because that's what we're going to be comparing to the products of each of the probability of A and probability of B, respectively. If you were to do that, just the 5/16 times by the half, that would get you 5 over 32, and that is not the same as 1 over 8. Therefore, in general, we are saying that they are not independent. Alright, so then just to wrap up with, we'll just see another example of a type of question that still uses this Venn diagram notation, but isn't necessarily a Venn diagrams question in another sense. We are also going to see this notation, just FYI, when we come to tree diagrams as well, potentially, but this is again like a third example. It's more just probability in general, like conditional probability questions. Here you have a table that's describing books in someone's bookcase. So we've got fiction versus non-fiction, and then if they've been read versus if they're unread. And for a key, we've just got the P of F means the probability that it's fictional, and the P of R is the probability that it's been read. So from this and from the table, find the probability of F intersection R, the probability of not F, and the probability of not R given F. This, I would just like to see how you can get along with it on your own, like we had with the other question on the other screen. Just pause the video, think what the notation means, think how you can apply it to the table, have a go for yourself, and then press play again when you're ready to compare. So, to start off with, if we're looking for F intersection R, we're looking at, out of this table, which ones are both fictional and have been read. Well, from here, that box would be this 20 here. However, because this is probability, it's not just enough to read off that 20. We have to take this 20 out of whatever the total is. So we are also going to have to add up these 4 numbers here. If you do that, you get 115. And 20 over 115 just simplifies to 4 over 23. Next, for the probability of not F, in other words, the probability that any chosen book is non-fiction, without any relation to whether it's been read or not, so anything out of these, again it's out of the total, so it'll be out of the 115, add these two numbers together to get the total number of books that are non-fiction, that's going to be 74, and 74 over 115 doesn't simplify, so we'll leave that one as is. And finally, not R given F. So what's the probability that it's unread given that it's fiction? Since it's a given that, we're no longer looking at the whole table, we're just looking at the fiction section, so these two numbers, so it's going to be out of 41, or out of these, which ones are also unread? That's these 21. So 21 out of 41 would be that final probability that you needed.